Welcome to lesson number 31. This is on aseptic processes overview. In this lesson, we will be looking at sterile manufacturing, sterile products, aseptic processing, and personnel. Sterile manufacturing. Certain pharmaceutical products must be sterile. These include medicines for injection, ophthalmic preparations, irrigation solutions, hemodialysis solutions, some medical devices, for example, hip joints, pacemakers, stents, etc. Sterilization refers to any process that eliminates, removes, kills, or deactivates all forms of life. In this case, it's referring to microbial growth in drug products and medical devices. Examples of product manufactured aseptically: large and small volume parenteral medicines, injectable vaccines. Some specific examples include Prograf, which is a prevention of organ rejection drug, and it is supplied as a sterile liquid. Remicade is used to treat types of arthritis, psoriasis, and Crohn's disease, and that is supplied as a sterilized lyophilized powder. Sterile products. Steam sterilization is non-toxic, it's inexpensive, it's rapidly microbicidal, sporicidal, and it rapidly heats and penetrates most packaging. In the past, most medical and surgical devices used in healthcare were made of materials that were suitable for steam sterilization. With increases in technology, advanced use of alternative materials, and the increase in biopharma, low-temperature sterilization is becoming more widely utilized. Many products, particularly biopharmaceuticals, contain constituents which are intolerant of heat. For example, proteins are susceptible to denaturation with heat. In these instances, filtration combined with aseptic processing is used as a mechanism of sterilization. Sterile production requirements. Production must be done in clean areas. There has to be an appropriate standard of cleanliness. The air must be filtered using HEPA filters, and there must be airlocks in place for entry so that you can manage personnel and/or equipment and materials moving in and out of areas. There needs to be separate areas for operations, so you would have a separate area for component preparation, your containers and closures, and a separate area for your product preparation where your filling and your sterilization is occurring. Pharmacopoeia requirements. The United States Pharmacopoeia, the USP 71 on sterility, defines requirements for sterility testing. It is harmonized with the EU Pharmacopoeia and the Japanese Pharmacopoeia. This means that the requirements are the same in all three. It states that the product must be incubated in an appropriate media for 14 days. No microbial growth is permitted in order for the results to be passing. For media fills, it is also 14 days, and again, no microbial growth is permitted in order to receive a passing result. This demonstrates that the products are sterile and that they are suitable for distribution. Sterile production environments. Preparation operations should be performed in controlled environments. So you've got different grades. Grade A is associated with high-risk operations, so where you're filling, you're doing aseptic connections. It's usually done in unidirectional airflow systems, such as a laminar airflow, and the air is appropriately filtered using a HEPA filter. Grade B are used in the background environment to a grade A, so in the case of aseptic preparation and filling. And grades C and D then are clean areas for less critical operations. Sterile production gowning requirements. In grade D, you would be expected to gown with your hair, your beard and mustache covered. You would be also expected to wear protective clothing and protective shoes. Grade C, the requirements will be a little bit more stringent. You would need to cover your hair, beard, mustache again, and you would be wearing a single or a two-piece suit covering your wrists and with a high neck on it, also covering shoes and having no fibres to be shed. Grade A and B is a more stringent requirement for your gowning. Here you would be required to wear headgear, beard and mustache covered, masks, gloves. There could be no shedding of any fibres, and clothing must retain particles shed by the operators. So no skin scales, hair or anything like that could be allowed into the process. Aseptic processing. There are two categories of sterile products. Those that can be sterilized in the final container, terminally sterilized, and those that cannot be terminally sterilized and must be aseptically prepared. So, for example, where you have biopharma or where proteins are being manufactured and they would denature from the heat required in final sterilization. Sterility assurance level, SAL. Sterilization is the act or the process that destroys or eliminates all forms of life, especially microorganisms. The probability of having one surviving organism in the load is referred to as the sterility assurance level, the SAL. To achieve a SAL of 10 to the minus 6, you need to demonstrate that the probability is less than 1 in 1 million of having a surviving microorganism in the load being sterilised. And down here in your diagram you can see for sanitization you're getting 10 to the minus 2, for disinfection level you're getting 10 to the minus 5, and for sterilisation with nothing remaining 6 log or 10 to the minus 6. Sterilisation production. The methods of sterilisation. Moist or dry heat, irradiation using ionizing radiation, sterilising gaseous agents such as ethylene oxide, filtration with subsequent aseptic filling. These are the 4 methods of sterilisation. Dry heat sterilisation. The British Pharmacopoeia references a temperature of 160 degrees Celsius for 120 minutes. That can be generally used for depyrogenation of glassware in order to remove pyrogens and endotoxins. Typically, the conditions are 250 degrees C for 30 minutes. That gives you a quicker turnover of equipment. There are 2 types of dry heat sterilisers. You can have a batch steriliser, which is a hot air oven, or you can have a tunnel steriliser, which is operated continuously as product is passed through a heated oven on a conveyor belt type system. Hot air sterilisers look typically like this. So you can see here we have what you might see in a batch scale for a lab. Here we have an industrial batch scale, and then this is what a tunnel steriliser looks. So you can see your conveyor belt here as you're going through. Moist heat. Moist heat kills microorganisms by denaturation or deactivation. It is applied in the form of steam. It uses saturated clean steam, i.e. so it contains the maximum amount of moisture without having any liquid condensate. Steam under pressure is used to achieve a higher temperature. The British Pharmacopoeia references a temperature of 121 degrees Celsius for 15 minutes, so that is a sterility assurance level of 10 to the minus 6 at 15 psi, so that's your pressure reading. There are 2 configurations for your moist heat sterilisers. Steam out of place, SOP, for portable items. Autoclaves are automated closed systems that use steam sterilisers, and we'll be talking a lot more detail about them in a further lesson. They use a temperature of 121 degrees Celsius for 15 minutes. The second type is a steam in place, SIP, and that's for fixed equipment which needs to be connected to utilities for the service. So, for those of you who did microbiology in school or in college, you might be familiar with the lab scale items used. In the industrial scale, you've got much larger items here on the right. You can see mobile unit bioreactors and filter housing as well. Personnel in sterile manufacturing. All personnel involved in aseptic processing operations must be trained and fully understand. They must understand the concept and the principles of GMP. It's extremely critical in their job. They must understand the relevant elements of microbiology, the importance of personal hygiene and cleanliness, appropriate gowning techniques for the area in which they work, the consequences of possible product contamination, the importance of reporting any illness or infection, including things like open lesions, coughing, sneezing, or any other conditions which could result in the shedding of abnormal numbers of particles or microorganisms, and in that case they would need to remove themselves from the area if appropriate. Personnel will be routinely microbiologically monitored, and they do this by taking test samples from gloves, from gowns and from face masks to ensure that people are gowning correctly. Documentation should specify and record the numbers and the type of operator interventions that are permitted during processing and in what circumstances they are allowed to take place. Personnel during validation activities. So, during validation, every attempt must be made to keep validation activities as close as possible to the routine manufacturing. So this includes all the criteria we've outlined in the previous slide, so what we said before in the previous slide, so adopting the same techniques and the standards of hygiene, the number of interventions that you are allowed to make with the process, the clothing that you're wearing, the number of people that are allowed into the area, and any behaviour needs to be kept as normal and as close to the regular routine manufacture in a validation study. In that way you will capture the worst case scenario and the normal routine. References and further reading. So there are some further readings here for you to have a look at. If you have access to the USP, Chapter 71 is on sterility, that would be in the library. The EU Regulations Annex 1, the EU Guide to GMPs, is linked here. Pharmaceutical Engineering Guides for New and Renovated Facilities, Volume 5. Guidance for Industry, Sterile Drug Products Produced Aseptically, Processing in Good Manufacturing. So it's an information guidance from the FDA. Over to you. What are the different methods of sterilization? What are the particular considerations personnel working in sterile manufacture must take? Thank you very much for your time and attention. We'll see you for the next lesson.